Hello, ninth graders. So we are going to finish up our 7-3 notes today. So we're going to finish talking about probability. So where all of this tends to lead of what we've been talking about is something called conditional probability, which will show up again in future years when you talk about probability in IB. So conditional probability is this idea that you want to find the probability of something given a certain condition. And we've already seen it pop up quite a few times with a few of our problems. And I haven't really truly explained like how we calculate that as an equation, which there is an equation for conditional probability. So you've seen it in our very last part of our previous example, the probability of A given B. And in our previous notes, I explained to you that like the given B part is the world that we're living in. If we're given B, we're looking at this Venn diagram and we're looking at the bubble that is specifically B and seeing, okay, well, there's 5 total things that could be happening within the bubble of B. And in that probability, in that world, of B, where you see in the denominator over 5, the probability of A in that world is 2 out of the 5. So what we do in terms of the equation is, let's get a different color going here. And I have a new pen just in time for the end of the school year. So we'll see if it works. So what we want to do in order to find the probability of A given B is the probability of A and B. So you'll notice that here it's 2. So if you go up to the Venn diagram, the probability of A and B is the part where they overlap. So 2 divided by the probability of B, which is 5. So that's your equation of the probability of A given B is that whole thing. So we're going to now implement it in these problems right here. So now we've seen how we can use it in a Venn diagram. And so for the rest of the notes, we're going to talk about using it in tree diagrams because it's easier to understand in Venn diagrams. But if you use tree diagrams, it's a different way of potentially dealing with more complicated conditional probabilities because the above conditional probability is really straightforward and these next ones are not. And so you would have to use a tree diagram in order to make sense of it all. So Mr. Williams goes cycling on 3 mornings of each week at random. When he goes cycling, he has eggs for breakfast 70% of the time. When he does not go cycling, he has eggs for breakfast 40% of the time. Determine the probability that he went cycling yesterday, given that he had eggs for breakfast. This seems like a really, really complicated problem because we're looking at it as a whole. So what I would like for you to do is just deal with the first piece of this conditional probability. He either went cycling or he did not go cycling. So there is it's called like a bivariate. So there is there are 2 options here and they split off from that. So those 2 options can be represented as cycling or not cycling. Remember that our apostrophe up there is not of that. So C stands for cycling. It's good to label your variables. So we could say C equals cycling is what that's supposed to say. And then C prime is not cycling. Okay, from cycling or not cycling, there is the option of eggs or no eggs. So we go from there, from the cycling, we can say, okay, well, he either went cycling, and if he went cycling, he either had eggs or no eggs. So we'll say E equals eggs. E, we call it prime. E prime is called or is representing not eggs. And then with not cycling, he still has the option of eggs or not eggs. So when you go here and you try and fill in the probabilities, you need you can fill in the rest given what you know. So Mr. Williams goes cycling on 3 mornings of each week. How many days or how many mornings are there in each week? There's 7. So if he cycles on 3 of them, that means 3 out of 7 he's cycling. So you can go in here for our tree diagram and say, okay, well, the probability is 3 out of 7. And then the rest would be 4 mornings he does not go cycling. So then 4 out of 7 would be your other probability. When he does go cycling, so we're in this world right here. When he does go cycling, he has eggs for breakfast 70% of the time. So you could either write that 70% as a decimal, or you can write it as a fraction. I'm going to choose to write it as 7 out of 10. But no matter what, however you write it, as long as it's true to the math, it will work the same. So 70% of the time he has eggs for breakfast, which means 30% of the time he does not. So then filling in the remainder of this tree diagram is 3 out of 10. When he does not go cycling, so we're looking at this bottom branch of our tree diagram, he has eggs for breakfast 40% of the time. So I'm going to represent that as 4 out of 10. And eggs, not eggs, will be the remainder, 6 out of 10, the 60%. So this is the tree diagram, and then we're going to use this tree diagram to calculate the probability that he went cycling yesterday, given that he had eggs for breakfast. So we want the probability of cycling given eggs. So then here's where we fill in our formula. So that's probability of cycling and eggs, and then over the probability of eggs. Now we need to look into probability of cycling and eggs. Probability of cycling and eggs is 3 out of 7 and then 7 out of 10. That's cycling and eggs. And remember that the word and means multiplication. So that's going to be 3 out of 7 times 7 out of 10 over. Now the probability of eggs is that the part of this is that the eggs occur in 2 different places. We have eggs here, or we have eggs here. So we're going to have this issue, or this thing that we need to account for, is that there's a possibility of it's either cycling and eggs or not cycling and eggs. So there's 2 different words here that have 2 different operations. And, which is for each of these instances, it's either cycling and eggs or cycling and not cycling and eggs. And that means multiplication for those 2 probabilities, as you can see in our numerator for our previous problem. The or part is going to be your addition in between. So we're going to find the probability of cycling and eggs, the probability of not cycling and eggs, and then add them together. It's either this and this or that and that. And that's dealing with your entire probability of eggs. So going in here and writing it out, the probability of cycling and eggs is again going to be 3 out of 7. Whoa, that was me trying to not look. Three out of 7 times 7 out of 10 plus, and then not cycling and eggs would be 4 out of 7 times 4 out of 10. So what that turns into is 3 out of 10 over, or 21 over 70 over, and then that's, let's do that instead. We're going to do we're going to do, just because I want a common denominator, because it makes things easier, 21 out of 70 over, and then it's going to be 21 over 70 plus 16 over 70. So I'm going to do a few things here. I'm going to realize that I've got fractions divided by fractions, and I know that if I'm dividing a fraction, I'm going to have to keep I don't know how you guys say it, but it's a keep, change, flip of you keep the first fraction, you change the division into a multiplication, and then you flip the second fraction. So we keep the numerator to be 21 over 70 times, and then 21 plus 16 is 37, so it'll be 37 over 70, but I need to flip that because we're dividing fractions. So it's going to be 70 over 37. And then from there, it's going to be a little bit easier to see that we just cancel out the 70s on top and bottom, and we're left with 21 over 37. 21 over 37. Okay, there, let's practice it again. On any given day, there's a 60% chance that Mr. Quelty will watch Coco. If he watches it, there's an 80% chance that he will cry. If he does not watch it, there's still a 30% chance he will cry just thinking about it. He's a very sensitive man, Mr. Quelty. So we have the probability he's either going to watch Coco or not watch Coco. The issue is that we have two C things, right? Coco and cry. So I'm going to have C be equal to Coco. So C prime will be not Coco. And then I'm going to have W be equal to cry. W will be weep. Okay, so on any given day, there's a 60% chance that Mr. Quelty will watch Coco. So I'm going to either have Coco or not Coco. And then we also have he will either cry or he will not cry for both of them. Going in here and filling out my probabilities, let's do um, 60% chance they will watch Coco. I'm going to do that as a fraction again. So 6 over 10, which means there's a 40% chance that he will not watch Coco. From there, then if he watches it, there's an 80% chance he will cry. So then 8 out of 10 for crying and Coco versus the 20 remaining percent that he will not cry. If he doesn't watch it, there is still a 30% chance he will cry just thinking about it. So then that will be 3 out of 10 versus the 70 remaining percent. Okay, so there is your tree diagram that represents all of the different situations and the probabilities that go with all of them. So what is the probability that Mr. Quelty cried yesterday? This is just the probability that he cried. So we need to go through and figure out, where did he cry? Well, so he cried in this situation. He also cried in this situation. So there's either this or that. So you need to find the probability of each of them and then add them together. So the probability of Coco and crying is here. 6 out of 10 times 8 out of 10 plus not watching Coco. Oh, I don't know why I did 7. 4 out of 10 times, so not watching Coco and then crying would be 3 out of 10. So this is not conditional. We're not talking about any certain situation. It's just, what's the probability that I cried? Okay, so that's going to be 48 over 100 plus 12 over 100, which is 60 over 100. So there's a 60% chance, or 0.6, or 6 out of 10, or 3 out of 5, however you choose to represent that probability that he cried yesterday.